Okay, welcome everybody to the University of Waterloo's Distinguished Lecture Series. Today our speaker is Oren Etzioni. So ever since I was a graduate student myself over 2 decades ago, I have looked up to Oren. So I am particularly delighted to have the opportunity to introduce him today. So an exhaustive enumeration of all his accolades would take far too long, so here I'll only hit on some of the highlights. So Oren has been a professor at the University of Washington, the other UW, since 1991. And since 2014, he has served as the founding CEO of the Allen Institute for Artificial Intelligence, whose mission it is to contribute to humanity through high-impact AI research and engineering. So Oren is an accomplished researcher, most recently a pioneer in machine reading and open information extraction, today what we would call knowledge graph construction. He's also a successful entrepreneur, translating his research into several startups, 2 of which were later sold to Microsoft and eBay. Oren has received numerous awards, including my favorite, being named Seattle's Geek of the Year in 2013. He's also a fellow of the IIII. So without further ado, Oren's going to talk to us about Semantic Scholar, NLP, and the fight against COVID. Please take it away.
Thank you, Jimmy. I appreciate the opportunity and your kind words. Of course, if you were a grad student 2 decades ago, people can do the math. I was a grad student even longer ago, but let's not dwell on ancient history. I was really looking forward to visiting the other UW in Canada, and of course we can't do that. But I do hope to come visit you in person when possible. And with that, let's get to my talk. I'm going to start with a very broad and important question. Is AI good or evil? And I'll talk about some of the debate around that. I'll then tell you a little bit about the Allen Institute for AI, or AI2 as we call ourselves. I'll delve into Semantic Scholar in particular, our scientific search engine, which is quite unique and quite popular. I'll then describe how our abilities in Semantic Scholar led to the construction of the COVID Open Research Dataset, COVID-19, and I'll end with some speculations about AI and science in the future. To make this a little bit more interactive than usual, I will try to pause for questions at least a couple of times during the talk at different sections. Hopefully this will work for us. And again, if the gods of the internet are kind, I'll also be able to show you a couple of fun demos. So let's do it. The first thing to realize is that for many people, AI evokes fear. And this isn't just, I don't know, the unwashed masses, people who are ignorant. It's plenty of people who arguably should know better. So we have folks like Elon Musk saying with AI, we're summoning the demon. Religious imagery, talking about how AI could destroy the human race, all of humanity. And we have folks like Bill Gates and others who have made similar statements. And you might say, well, okay, well, these people don't really know about AI, but we also have folks like Stuart Russell at Berkeley, who is an AI researcher, longstanding AI researcher, and he argues some of the same points. On the other side of this discussion, we have folks like famous roboticist Rob Brooks, who says if you're worried about the Terminator, just keep the door closed. AI is not nearly as advanced as some people think. And of course, through the success of reinforcement learning, this robot will eventually figure out how to open the door, only to find out that there's a staircase behind it, and our robots struggle to climb staircases. And we'll solve that only to find out that there's another challenge and yet another challenge. The truth is that our AI systems are these savants. They're very good given training data at solving narrow tasks, but they're not very strong in general. And so Stanford's Andrew Ng says, working to prevent AI from turning evil is a little bit like disrupting the space program to prevent overpopulation on Mars. It ignores both the technical difficulties. We haven't gotten anyone on Mars yet. It's really quite a challenge. And it also ignores the potential benefits. The ways things are going with climate change and political upheaval, some of us can't wait to get to Mars. But my point is that this is really a subject of intense debate in various quarters. It's a question that goes all the way back to the Golem and Frankenstein. And not only is it not going away, but it seems that the progress we have been making as a field makes the question more and more acute in people's minds. So I want to be clear that when I'm talking about the question of AI good or evil, I'm not talking about issues like AI's effect on privacy or the bias that's occasioned by it, or even its economic effect in terms of jobs. These are all very important questions. I'm really talking about this very fundamental question. Is AI going to destroy civilization as we know it? Is it an existential risk for humanity? And I had a conversation with Max Tegmark, who's a thinker on this topic from MIT. He wrote a book called Life 3.0. And I try to say, you know, Max, I feel like this discussion of AI annihilating the human race is distracting us from more practical, pragmatic questions like, well, what are we going to do about all the people who are going to become unemployed due to the advance of technology? Let's say truckers, once self-driving cars are rolled out. And he said to me, Oren, I'm talking about the fate of humanity, and you're arguing with me about what should we feed the kids for dinner. In other words, he's saying, look, those questions are relevant, but they're kind of mundane and short term. You got to think about the fundamental questions. And so, as you can see, we can bandy intuitions and argue about this philosophically really endlessly. I could give a whole talk on the different arguments that people make. But earlier this year, in an article I wrote for MIT Technology Review, I tried to put this on a more empirical footing. I said, you know, can we identify some tripwires, some canaries in the coal mine? I call these canaries in the coal mines of AI. That if these canaries keel over, then we'll know, okay, human level intelligence, super intelligence is around the corner. But if that doesn't happen, then we really don't need to worry about it. And AI is much more a technology like software. We continue to develop it, improve it, make it more sophisticated, but it's not something that's going to take over the world. So I believe that that is very much the case. Mark Andreessen famously said that software is eating the world. And I would say that machine learning is eating software, right? We're using machine learning more and more across the board. But we have to remember, as I think all of you know who actually work actively with machine learning, it's 99% human work, right? We have to define the inputs to the system. What's the data set, labeling the data, what's the algorithm that's being used, what's the concept that we want to learn about. And very importantly, we have to assess the output. And if that's not good, we go again, right? It's very much an iterative process, and building machine learning models in a funny way is not unlike debugging. It's very much programming, very much human work. And the machine really does the last mile. Once you have all this done, the statistical computation of what model best fits the data, yep, the machine does do that. And so in a funny way, machine learning is really a misnomer. And it's a misnomer in a field full of misnomers, right? Like artificial intelligence. And I like to say that saying that machines learn is really like saying that baby penguins fish. What actually happens is the parent penguin goes off into the water, corrals fish, finds them, hopefully successfully catches them, eats them, and then presents the baby with a regurgitated morsel right out of its mouth, as you see in this little clip, and then the baby eats that. So baby penguins don't fish, and machines don't really learn. So with that in mind, we're ready to define our first AI canary. What if we had a machine that really genuinely learned much more at the level that a human does? So let's say we have a machine that can automatically formulate a machine learning problem, basically do all the pieces I described, the 99% of the human work, and formulate the machine learning problem for itself. It would be part of what's sometimes called universal subgoaling. Let's say I'm working on something and I need to realize, hey, I really should learn PyTorch to do that. So I subgoal on learning PyTorch. And then I've learned that, and now I realize, okay, I want to learn Al2 which is a framework on top of that. So I learned that. And then I say, well, I really need to understand how self-attention works, and so on and so on. So we're constantly, as humans, coming up with ideas, subgoaling on subtasks, learning what we need to do, and then returning to the original task. And that's a very complex and involved process that's done independently. We can get help from peers or from books or from teachers. All of this is completely different from what the machines do. So the bottom line here is that AI is a tool or a set of tools, and it's not a being or a creature, and it's up to us to employ this tool to benefit humanity, as opposed to worrying that some being will take over the world. And with this, I will pause before I move into more practical topics and just see if people have any questions, comments, or reactions. And I'll rely on Jimmy to let me know if something shows up in the chat, etc.
Currently, you seem to have universal agreement, so why don't you just proceed?
Okay, you know, I sometimes think, gosh, I'm preaching to the choir when I say this, particularly if you're hands-on. But again, there are people in our field, and Stuart Russell is probably the most prominent example, who really think otherwise, who think that we are being complacent. So I think this point is worth making. But focusing now on using this tool, using AI for good, the late Paul Allen founded a nonprofit research institute in 2014 that I run, as Jimmy mentioned. Its mission is AI for the common good. And over the last 6 years or so, we've become leaders in research on computer vision, natural language processing, and deep learning. We've published, actually, I should correct that, more than 400 papers in premier conferences. We've gotten a bunch of best paper awards, and we have over 100 PhDs, researchers, and engineers, very robust intern program, et cetera, et cetera. And we are continuing to hire even in this time of COVID. So I should mention that we're located in Seattle, although we have a small office near UC Irvine and another one in Tel Aviv, Israel. So there's a whole bunch of projects at AI2, as we call ourselves, and I'll just mention most of them briefly in a sentence or two, and then we'll delve into Semantic Scholar. So Mosaic is one of our most exciting futuristic projects. It's led by Dr. Yejin Choi, who shares her time between AI2 and UW, and she's asking the question, how do we endow machines with common sense? And that's a question that for a long time, Doug Lenat and his team at Psych was the only one trying to ask that question. And he was asking it using really technology from the 80s, knowledge engineering, basically typing a large number of bits by hand into the machine in a fairly heavy logical language. That didn't go so well. Yejin and her team are trying to do this using modern techniques, including machine learning and crowdsourcing and so on, and have been getting some very good results, including winning the Best Paper Award at IIII this last year. That's not a result, that's a recognition of some of the work they've done. Again, very futuristic stuff. It's not even clear how you would define or decide whether a machine has common sense. The Aristo project focuses on reasoning over information obtained from text. So often our systems do rather simple things with representations like Elmo and Bert, but how do you reason on top of that is a big focus for Aristo. The Allen NLP project is focused on modern NLP research. It's led by Noah Smith, who also shares his time with UW. I should mention Aristo is led by Peter Clark, who's a senior AI researcher. And NLP also has an open source platform that's really very handy if you want state-of-the-art models to use as baselines for your research and to iterate from there. The prior team is our computer vision team. It was led by Ali Farhadi, except that one of the cool things you can do while you're at AI2 is launch companies, kind of like, Stanford launched Google, and a lot of universities can incubate companies. We make that particularly easy, and so Ali Farhadi launched a company called Xnor, and it bought it for, Apple acquired Xnor for a reported $200 million or so. So that was a great success for everybody. Unfortunately, they also bought Ali with it, so he no longer runs the prior team, but the team continues to be very successful under local leadership, as it were. And I mentioned the incubator, so let me now turn and tell you more about Semantic Scholar, which is at the core of our talk today. So Semantic Scholar is a program that we developed just about 5 years ago. We started working on it, and it attempts to address information overload, particularly for professors. So we all suffer from information overload, right? Tweets, Facebook posts, emails, Slack messages, new items on Spotify, you name it. We're just inundated. Well, academics, in addition to that, have to deal with 8 million new papers that are published every year. The number of papers published is doubling every few years. And studies show that scientists only really read on the order of 200 papers in a given year. So clearly we need some good tools to help us choose the right papers to read. And that was the motivation for Semantic Scholar. We thought, let's use AI and information retrieval, NLP, and a host of related techniques to really home in on the key papers and results and help you to cut through the clutter to find what you need to do to be a successful scientist. So at this point, 5 years later, the corpus, the Semantic Scholar, contains on the order of 190 million papers. We have more than 8 million users per month, which we're particularly proud of because as a nonprofit, we don't have a marketing budget, so it's very much word of mouth. And it covers all academic disciplines, excuse me. And I'll tell you a lot more about Semantic Scholar now. Basically, what we do is we take the PDFs, which are how papers are represented typically, and we map them to a literature graph where the nodes in the graph are papers and individuals who write the papers, individuals who cite each other, and so on and so on. We provide search capability using keywords and metadata, similar to Google Scholar and other scientific search engines, hopefully somewhat better in various ways. We have a different approach to ranking. And we have paper detail pages. So every paper and every author have their own page. And our paper detail pages, think of a Wikipedia page but not for an individual or for a rock group, but for a paper. So it contains not just the PDF, but also links to blog posts and news about the paper, videos maybe of the person presenting the paper, a slide deck or several slide decks about the paper, links to GitHub repos where you could have the associated code, and so on and so on. So it's really meant to be the ultimate destination if you want information about the paper. In addition to that, we've been quite innovative in terms of thinking about citation metrics. So first of all, we don't just count citations the way everybody does, but we also look at the number of citations per year. That's the velocity of citations. And we look at the derivative of that, citation acceleration. That's the change in the number of citations per year. And I'll show you how that makes a difference in a second. But even going beyond raw citations, we find a more semantic notion of citations where we exclude self-citations. And we know, by the way, that men tend to cite themselves 20 to 30% more than women do. So our notion of citations is more gender neutral. We also exclude incidental citations, the kind of citation you add in the paper out of politeness or completeness. Oh yeah, I should cite that, but your paper really doesn't build on it. And then we rank the citations by the degree of influence. If I have two papers, our NLP models analyze the papers, and it'll determine whether paper A really builds on paper B, or whether it kind of mentions it pretty casually. I wrote a little bit more about this in a short note that appeared in Nature in 2017, and again, I'll demo this shortly. So I'm going to show you now a whole slew of features of Semantic Scholar, but before I do that in the demo, I want to kind of present a model of how we think about how scientists engage with scientific papers. And basically there are three phases. The first one is the discovery phase. You have to find out about the paper. You might find out about it socially from Twitter, or maybe somebody sends you an email about it. You might find it using a search in a search engine, or you might be browsing through a conference proceeding or some other lists and you come across the paper that way. For this first phase of paper discovery, as I mentioned, we have search. We also have a notion of recommendations. So recommendation technology in AI has been applied to products on Amazon or to movies on Netflix, but we've actually built a paper recommendation system, which is quite an interesting topic because it requires computing similarity between papers, and papers are rather complex objects. We also have developed a research feed. So again, many people have a Facebook feed or a Twitter feed, a news feed. We have a research feed that you can constantly tune to your liking based on, hopefully you can see on the slide saying, I like this paper, I'm not interested in this paper, and you can get alerts on papers on a particular topic of interest to you. So that's how we support discovery. The next step, once you've discovered a paper, you have to make a key decision. Do I ignore it? Do I skim it, maybe look at the abstract, glance at a few figures? Or do I actually read it? Do I make it one of that set of 200 or so papers that I read? And to support the reading decision, obviously we have abstracts, but we also highlight the key sentences in the abstracts to make that easy to read. As I mentioned, we automatically extract the figures and the tables in the paper, and that's particularly handy when you're on your phone. You don't need an app. You just go to semanticscholar.org and you can quickly flip through the figures and tables to decide, hey, I should save this paper for reading later, or maybe just remind yourself, oh yeah, they got 83% on this data set. When we look at the citations, we filter them, we analyze them, we sort them by the degree of influence, and we also give you citation excerpts. One of my favorite ways to decide whether I want to read a paper or not is to see what other people said about it when they cited it. So that's something we support, and I'll show. And then lastly, something that we just launched, it's actually only available on Semantic Scholar in a A/B test, so not everybody will see it, but it'll be coming out shortly. And it's a topic of a paper we published in EMNLP, is what I call extreme summarization. And that's the idea, can you take a paper and summarize it basically to one sentence, a TLDR for the paper. So I'll give you an example here. Here's a famous paper from 2017 about self-attention. And the TLDR that was automatically computed here, I don't know if I'll read it in case you can't. It says, we use a 2D matrix to represent the embedding, with each row of the matrix attending on a different part of the sentence. And this is generated fully automatically using a generative language model. Think of it as something akin to GPT-3, but tuned for scientific summarization. So again, lots of different things to help you make that critical decision. So now let me turn to my demo. So hopefully you can still see this. So I have here Semantic Scholar. Let me start here. So if I click on Jimmy Lin, so I want to get caught up with his research. I click on that. We have autocomplete. As you can see, author disambiguation is a hard problem. So let's say I click on this one. Looks like I got the wrong Jimmy Lin. Right, this one works on biology and medicine. So I go back and I go to this one with 258 publications. Jimmy, you've been busy since grad school. And again, I have to confess, we probably haven't gotten all of Jimmy's papers even because some have been maybe assigned to the different one. So let's look at this, what we call the author homepage. First of all, if you click here, you can see what we call an influence diagram. So what I'm showing here is the different people who influenced Jimmy. And perhaps not surprisingly, you see W. Croft and Ellen Voorhees, and then you look at the people that he's influenced, and okay, here's a bug, right? He's influenced himself. That shouldn't be the case, but J. Rao and so on. And if you're wondering, well, why do we think that? Then we can look at the papers and see what are the papers this person has written that were influenced by Jimmy's work. And we can navigate this graph recursively. So now I've clicked on Tina, and I can see her work, and so on and so on. So it's a great way to navigate this author graph. Let's go back to Jimmy's work. And so this is his author homepage. It's sorted by his most influential papers, right? So overview of the micro blog track, some work that he did back at Microsoft Research, maybe as an intern. And I might be interested in more recent stuff. So of course I can also sort by recency. What has he done for us lately? Or I can sort by citations per year, right? The velocity. So it seems like this paper on PICO as a knowledge representation for clinical questions, I hope we have the right Jimmy here, is getting quite a few citations per year. And then I can click on this paper. I haven't done this before. I want to learn more about it. So I click here, and I can quickly see, all right, let's have a look at the tables here, number of questions. Okay, these are the sort of structural pattern examples, et cetera, et cetera. So I can quickly see whether this is a paper that, that I might want to read or not. And then if I go to the citations, it's got 373 citations. Again, I can filter those in various ways. I can sort by the papers that were most influenced by this. And I see, for example, a variety of papers. And here, if I go to this one, I could look at excerpts of the different citations. So what do they say about this paper? Again, the excerpts aren't terribly interesting at this point. If I go to my research feeds, you can see that I have two. One is about common sense knowledge, and one is about literature-based discovery. I can also click there and see the recent archive papers that the system recommends to me. And okay, this one I like, so I'm going to say more like this. Or let's see, this one I'm less excited about. I say less like this, and I can quickly go through them and say, okay, this one on term extraction, I definitely want to save in my library. I can save it under tags. So a rich feature set for discovering papers, for managing them, and so on. I just want to show you one other aspect of this. So let's say I look for Green AI, which is a paper that we wrote a while back. So if I click on that, you can see that a lot of this ancillary content that I talked about, I can go to the code associated with that paper, or I could look at mentions of that paper in the popular press. Here's, there was an article about it in the New York Times. I can read about that, or here's a blog post about it in Forbes, so on and so on. So just a lot of stuff to help me decide do I want to go ahead and read this paper? So again, at this point, let me stop. I've been talking for a long time, showing you the demo. Any questions or comments about Semantic Scholar?
And by the way, yes, that is my paper.
Oh, good. Yeah, it's a surprisingly difficult problem to tease people apart. We are rolling out a major improvement to our author disambiguation, but it is hard. I'm glad that we got that one right.
All right, please continue.
Okay, our again experiment in question answering. Hopefully, people.
Oh, sorry, we have two questions that came in. Did you mind taking a few seconds?
I don't mind at all.
Okay, how do you rank papers is one question.
I'm really glad you asked that, because the ranking function is a learned function. We use a deep learning model based on label data and click data. But I'll tell you one thing that we do that I'm rather proud of, which is very different than Google Scholar. And that is we rank papers less by the number of citations they've gotten and more by the citation velocity and citation acceleration. And the reason is that you'll have a paper, and typically, if it's a paper from 2003 or 2008, or God forbid 1992, it's had a long time to gather citations, so it may have more citations than a more recent paper. But we really need to think about the rate it's being cited, effectively normalized for its age. So of course we use information retrieval and keywords, but we also look at citation counts very differently. And if you want to see a very stark example of that, take the word attention, right? A very standard technical term in deep learning. And if you go to Google Scholar and you type attention, you'll see very different results than if you go to Semantic Scholar and type attention. So that's, again, one of the important principles. We think we can give you more current, more relevant results based on our citation metrics.
And a related question as a follow-up. I think this is, you already addressed this, but the question was, what do you use for training the models involved in Semantic Scholar? So click data, and you mentioned other data. You want to elaborate on that a little bit, please?
Yeah, sure. So it's actually a really interesting and tricky problem, because so in the ranking case, it's relatively straightforward, but we have a lot of models that are much more sophisticated. So let's take the TLDR model. What we did is we worked hard to create a data set. And by the way, as a nonprofit, all our data sets and our various research efforts are open source and publicly available. So we created the world's largest TLDR data set, meaning a paper and a human-generated TLDR for that paper, either by the author or by a reviewer. And we use that to tune our method. When we do information extraction, we extract key information from papers. Again, we've had to work to create data sets for that. And let me tell you that you can't use Mechanical Turk to get extractions from scientific papers. So we've invested a lot in creating these data sets, but the good news is often you don't have to. You can leverage our work if you want to do research in this area.
And finally, one more before allowing you to move on. So you mentioned data sets. Can you describe a little bit in a little bit more detail the data acquisition process? How are you crawling? What databases you're pulling from, et cetera?
Sure. So our corpus is compiled of several sources. The first one is we do have a web crawler. So we're out there looking for PDFs, both of papers and slides. And then, of course, we have to filter them. Secondly, Microsoft has generally shared with us the Microsoft Research Graph, which contains a lot of information that the Bing crawler has found. We then map that to data sources in various ways to clean up that. And then we have databases that we get from publishers, from preprint servers like Archive and bioRxiv. And so the combination of crawlers and databases and filtering is what gives us the 190 million entries that we have in our paper database.
Okay, great. And I'll let you move on. Thank you.
Sure, and I should add, again, because we're not a university, Semantic Scholar has quite a large team, and we do a lot of work that you really wouldn't want to do as part of your master's or PhD or undergrad research project. But the good news is that we make all that available via a set of open APIs for free. So if you want to have access to the data sets, they might be saved, or you can literally query our engine programmatically. So for example, there's a very cool website called Connected Papers, which is a visual discovery tool for research papers based on graphs. And the people who built that is just, 3 folks in Israel who built that using our API. So to continue the talk, I want to get to the third phase of the way we engage with scientific papers, and that's we've decided to read them. There's still phases in there, to how do we understand them, how do we retain what we've read, and we might even decide to cite them, which of course goes back into this feedback loop. The interesting thing is that we have relatively little support in reading papers, right? The way we read papers now is using PDF, and gosh, that hasn't really changed much since I was in grad school, way before Jimmy, where we had PostScript files, if anybody can remember that. And in fact, back in the cave days, right, there wrote papers on tablets on the wall. What's really the difference? These are sort of inert display formats. So in joint work with the University of California at Berkeley, this is Marty Hurst and Andrew Head, her grad student, and this is a work that's led by Dan Weld at AI2. We've built an interactive reading application that tries to help you understand a paper. So it automatically creates a glossary and helps you understand the paper's lexicon, how it relates to other papers, and the various mathematical terms. And I'm going to give an example. This is not yet widely available. Everything I showed you with Semantic Scholar is. This is still a demo, but we hope to have this out certainly by the beginning of next year for people to use. So this is an interactive paper reader. And the demo I'm going to show you is focused on the mathematical terminology in the paper, but we're in the process of extending that beyond it. So here is a rather famous paper at AI2 that was on the mechanism called BiDef. It's not really important, but what you see here is the glossary that was automatically generated of all the different mathematical terms. Makes it easy to refer to them and understand what's going on. And of course, this is the paper, bidirectional attention flow. As I read through it, I see there's a reference to another paper. I can click on that and immediately see, okay, here's who wrote this paper, here's their citations. Soon we'll have the TLDR, and I can even save it to my library if I want. So, and I don't have to go to another page. Then I can continue through the paper. And where things really get interesting is when I come across, let's say, an equation like this one. So now when I click on the equation, the different terms are defined for me automatically. And furthermore, if I want to look at a term, I can see the different appearances of the term in the paper. So this H colon sub T, I can go to the next place it's used, and the next place, and you can see here that now I've got other equations. A lot of this stuff is grayed out, but the key information, the attended context vector, is right here. So we really hope to revolutionize how you read papers over time. There's a lot of excitement at AI2 about these capabilities. So I've just described to you a whole host of features. And again, it's not always easy to retain all the specifics, but the bottom line is that we're using AI capabilities to make the process of discovering papers, deciding whether to read them, and then actually reading them better, faster, more efficient, more interactive. To do that, we found that we have to scale NLP from its current state to documents. So traditional NLP, well, it dates all the way back to Harris and the distributional hypothesis in 1956. But in recent times, it's focused on local context and on typically on sentences, right? So we work on parsing sentences, translating sentences, extracting information from sentences. And we've realized that we really need to think a lot harder about scaling that up to documents. And by the way, I don't claim that we're the only people to do that. That's far from true. But we found that we need to break new ground here. So let me give a very concrete example. The context notion in transformers, like in the famous BERT system, which by the way was based on a system called ELMO that was developed at IIII. I always want to mention that. We're very proud of that. Is based on 512 tokens. And if we want to base our analysis of words or tokens on the full document context, we need more. So we've built a system called Longformer that looks at 32,000 tokens, a significant scale up. Likewise, when we're doing question answering, we want to do that over the entire document. There's been a lot of work on question answering in NLP, but often it just focuses on a single paragraph or a single question. And we have to go beyond that. Actually, we want to be able to answer questions over a whole multi-document graph, right? So not just a single paper. And just to look a little bit under the hood, this Longformer technology, the reason it was able to scale from 512 to 32,000 is because it avoids computing the full attention matrix. So typical attention computation is n squared in the length of the sequences being attended to. And you can't do that with current technology in 32,000 tokens. And what we've done instead is figured out how to do that in linear time. And that's represented by the sliding window attention B. Turns out that that kind of local notion of attention is not enough. So we then added elements of global attention, which what you see is in figure D. We have a mixture of local and global attention. But the point is that that mixture is still linear time, which allows us to go a lot further. And there's a paper on this, the famous Longformer paper, which of course you can find on Semantic Scholar. In addition to thinking of long context vectors, we're also starting to work to use the structure that's in the document to help us, again, have stronger, more semantically accurate notions of context. So we look at the figures, tables, captions, papers that are connected via citation, et cetera, et cetera. So what's really going on here is that NLP is starting to come to terms with a major grand challenge. And you started to see scientific NLP get more and more attention. Recently at the major conferences, there have been workshops on it. And I think people are realizing, back when Twitter was created, I and others, were fascinated by how do we do NLP over tweets? But I think more recently we've come to realize that at least as important is doing NLP over scientific papers, because it's going to make scientists that much better at their jobs if we can help them. So with that, let me turn to the story of COVID-19. In March 6th of this year, the CTO of the United States from the White House contacted IIII via a colleague at Georgetown University and asked us to do the following. He said, we know you have this technology for building literature graphs and analyzing the papers. We want you to put together a machine readable corpus of all the papers on COVID-19 and all the related papers on coronavirus. There were studies of SARS and so on. And we said, of course, we want to help the medical community. When do you need this by? And he said, we need this yesterday. We're fighting the virus urgently. And I'm very proud of our team. Within 5 days, we created the first version of the corpus. We worked closely with partners at NIH, National Library of Medicine, BioArchive, MedArchive, and more. And within 10 days, the White House announced the release of the machine-readable COVID-19 dataset, and a number of groups started using it to create all kinds of systems. The original corpus had 24,000 papers. At this point, we have more than 200,000 papers in that corpus. It's being updated daily as more and more research comes out. And not only is the text machine readable, so you can build NLP and IR engines on top of it, but tables are machine readable as well. We have state-of-the-art technology for table extraction that was contributed by IBM. This became the basis for the most popular Kaggle competition ever. The data set has been viewed more than 2 million times, and a whole bunch of medical information has been extracted from it, a wide variety of places, including University of Waterloo. I believe it was Jimmy's team created systems that operate on top of COVID-19 to get researchers the information they need. So let me just give you a few snapshots. I don't have time to go into them in a lot of detail, but just give you the flavor of the many publicly available tools. There are question answering systems where you can ask questions like, what are prevalent antibodies in the saliva? Are IL-6 inhibitors key to COVID-19? And you get answers. Here's a snapshot of a system out of Korea University. Here's what the answers might look like. The question here is, what temperature kills COVID-19? And you have the answer 56 degrees Celsius highlighted. And if you look closely, you see that this system, at least in the snapshot I took, can also misunderstand the question, give the wrong answer completely. So it's important that not only is the answer highlighted, but you see the sentence. And of course, you can click through to the paper to verify the information. We also allow for claim verification. For example, it seemed to be controversial for the White House, at least before a bunch of them got COVID-19, that mass masking was important. So we're able to put in a claim to into SciFact, which is a system built jointly by UW and IIII, and again, identify where that claim is supported or refuted in various scientific papers. We also have used information visualization techniques. So this is a system called SciSite. It's available on our website, and it allows you to dig into COVID-19 to try and look at connections between proteins, genes, and cells. And when you find two items where you want to see the connection, you can click on the edge shown here in blue, and it'll take you again to the relevant paper. So a very different way of finding papers. It doesn't just allow you to navigate between papers, but also between groups that focus on different areas. Virologists have told us that they're very interested in understanding which group is working on what. So for example, here you see, if I choose the topic Ebola virus and the affiliation Oxford, not only do I see the groups in Oxford, but I see groups working on related topics. Those are marked with purple edges, groups with social affinity. In other words, they collaborate with the group in Oxford, and I'll see that with green links. And again, just a very powerful way of navigating the world of science. If you look at the bottom left, that's the URL you can check this on, or you can just go to our website. So our goal really here has been to connect the AI and medical communities. I'm really proud that there are more and more papers appearing in medRxiv and in scientific journals that build on COVID-19 and the tools that others like Jimmy and his team and quite a few others have built that use COVID-19 to provide information for medical personnel. I want to stop now and again see if there are any questions about COVID-19, and if not, I'll end with a few slides of more general speculation.
So there were some questions that came in after the last pause. Would you mind taking them now?
Not at all.
Okay, so can you say a little bit more about your definition of influence and how influential citations or influential papers get computed?
Yeah, so basically the notion of paper A influencing B is both intuitive and difficult to formalize, right? So the intuitive notion is when you have a paper, let's say, I don't know, I'm working on open information extraction, and I built on conditional random fields back in the day. I'm dating myself, but I modified it in certain ways, and I used a particular implementation, and I changed some things. But the open information extraction mechanism I use uses CRFs very heavily. So I might refer to it multiple times, and to details of it, I might cite it, I might compare to baselines in various figures. So the two papers are very deeply connected. What we've done is we've trained an NLP model that runs over my paper and assesses how much it was influenced by that other paper I'm citing that used CRF for information extraction. And it would contrast that with, let's say, I happen to use the Stanford parser. So I cited it. So I use that parser. I cite that in a footnote. Who cares? So those are the two extremes. Now, how do we determine the exact degree? What we've done is a pretty standard methodology. We labeled a whole bunch of papers and their relationships, and we trained the model that optimizes predictive loss relative to that labeling. But the basic intuition underlying the model is actually very simple. It looks at two key factors. One is, how often does paper A mention paper B? If I mentioned your paper, Jimmy, in one of my papers, I mentioned it 15 times. That's much more likely that I'm building on it in a key way than if I mention it once, right? Also, what sections did I mention? If I mentioned the related work section, sure, that's one thing. But if I mention an experimental results section, then probably I'm building on it quite directly. The second thing is, when I mention your paper, is it part of a long list, great work on IR by Jimmy and Ellen and all these wonderful folks. So it's a long list of citations, or do I mention it by itself? So all these different variables feed into our model and help us to define a fine-grained notion of influence.
Okay, great. That's an awesome answer. So we should let you finish your slides and then come back and circle back to see if we have any questions for the end.
Okay, so we're almost done here. What I want to highlight, and this is very much the vision that motivated us to build Semantic Scholar, is that we see AI as a basis for a next level of scientific discovery. And this level is where we have a tool that helps scientists deal with information overload, deal with these millions of papers. Imagine that a cure for an intractable cancer or some other disease is hidden within the thousands of reports on thousands of clinical studies, and nobody is able to read all this information. An AI-based discovery engine could help medical researchers find the answer. And of course, we don't just cover medicine or computer science. We cover all areas. So if we want to fight climate change, again, scientists working on that task can use Semantic Scholar. So that is really our vision, and it's very much a broad and expansive vision. Semantic Scholar is not going to have all the answers. We hope that others like you will join us in this quest. And now I want to go back to the question that I raised at the beginning of the talk. I think most, if not all of us, will agree that AI raises all kinds of complex issues around privacy, fairness, job displacement, and so on. But to this question of, is it poised to destroy humanity, as folks like Nick Bostrom and Stuart Russell, Max Tegmark say, I actually think it's quite the opposite. AI is poised to save human lives. My favorite example of that is intelligent cars. We have 40,000 highway deaths in North America each year alone. We have more than 1 million accidents with people hurt and injured. And studies project that we could cut the rate of injury and loss of life by as much as 80 or 90% once self-driving technology is available. So my answer to the folks that worry about AI as destroying humanity is that it's quite the opposite. In the words of Eric Horvitz, it's the absence of AI technologies that is already killing people. The absence of it in cars, the absence of it in drug discovery. And our job, our imperative is to bring AI to applications where AI serves the common good, serves to save people's lives. Thank you very much.
Okay, well, since you answered some questions in between, I will just have time to ask you a final question, and I think this is a great one to end on. So the comment is, whenever we automate something, people begin to forget how to do it, right? So will AI to help people read papers and discover scientific knowledge reduce our ability to actually do it on our own?
Well, I think that's a very fair question. And, you know, to the extent that if we look at arithmetic, I think that actually illustrates this well. So on the one hand, most of us haven't forgotten to use arithmetic. On the other hand, we're probably not as adept in it, because whenever I have an arithmetic question nowadays, I'll ask Alexa or Google, or I'll use the calculator in my watch or my phone, what have you. So I think that there is something lost, but usually it's traded for something better. Do I really need to calculate tips in restaurants, or can I use my time better, more creatively otherwise? So I don't think that for the foreseeable future, AI and Semantic Scholar is going to replace scientists. I think it's going to be a basic tool to extract information or to find papers that I want to read. Imagine if I can get results of studies from 100 papers with one queries, right? Let's say we have an SQL for scientific papers. That would be amazing. And it would enable me to do things that would take me an inordinate amount of time to do nowadays. So I think overall, all technology has a cost-benefit trade-off, but in this case, it's a very positive trade-off.
Okay, great. And with that, I think that's a great ending point. So once again, thank you for giving the talk, sharing with us your vision and your steps towards it. And wish you and AI2 the best in accomplishing that for all of the benefit of humanity.
Thank you very much. Thank you all for those of you who stuck it out and listened, and look forward to meeting you, catching up in person as soon as safe.
All right, take care.
Bye-bye.